Thanks you, NAE, for inviting me to give this talk. Kind of like to just tell you a little bit about the LED lighting revolution. The evolution of lighting, first man had fire, of course, and then we had Thomas Edison's light bulb, and now we have, of course, the compact fluorescent, which is widely seen in stores. And just now, in the past year, you can start to see LED light bulbs appear. And like Mark Pinto said, costs in the semiconductor technology are basically dropping 30 to 40% every year. So even though today's LED light bulb is about $25, $30, it will be a few dollars within a few years, and that's the story I'm going to tell you. So a little bit of background on the Solid State Lighting and Energy Center here at UCSB. Our main focus is on making ultra-high efficiency white LEDs. Currently, even at current technologies, we're 7 times more efficient than existing incandescent lighting technology. And since lighting consumes 22% of all electrical power in the US, this can really impact the efficiency of lighting, and we believe we can drop this number to about 5%. So that would be a huge energy savings. But we're also looking at forward-directed technologies, such as instead of using LEDs, even using lasers. And actually, BMW is already mocked up and is planning to release in 2 years a car using laser-based headlights, where the laser just is the pump source, but the phosphor ball is what's being projected, so it's not a dangerous headlight, but it's actually more efficient than the LED solution, turns out. Hopefully one day you'll see today the same things we use to make LEDs used as laser projectors for cell phones and TVs. And then finally, Umesh is going to talk about something that we started here almost 12 years ago, I think, which was we wanted to use gallium nitride, not just for LEDs, but also for power switching. And we went to DARPA, I think, and got our first funding was with Umesh. But we believe that even in the power generation side and the conversion losses, particularly switching power, we can save up to 10% of the electrical power, which is the conversion losses, and we'll hear about that. And even working on solar cells. So this material center here, we're working on a wide variety of technologies which impact energy efficiency. Again, this just kind of shows a pictorial aspect, is that we're using solid-state technology primarily based on gallium nitride, but we also look at silicon carbide and zinc oxide to address 4 applications that we believe could be impacted by this technology. I will focus today primarily on the lighting portion because that's the nearest term solution. And you'll hear later from Umesh and John Bowers about some of the other ones. So at UCSB, since Suji came in 2000, we've built up the largest academic effort in the US on LED lighting. And one of the biggest in the world. I believe there's one slightly larger one in China now in terms of head count, but we believe we're leading in innovation. Some of the faculty in our center, obviously Suji is sitting in the back row here. I was in Japan in '93 when he showed this extremely bright blue LED. And for those in the LED field at the time, it was about 200 times brighter than any other blue LED that had been made from silicon carbide. At that point, I literally called up my research group and said, we're going to add ammonia onto our system so we can start doing nitrogen. So I switched my research basically from indium phosphide to gallium nitride just after seeing this one demonstration. So that was kind of a fun history. Also, again, you'll hear from Umesh Mishra on the power switching side. Jim Speck and myself lead a lot of the material science that goes behind this LED light bulb. We also work collaboratively with Pierre Petrov on looking at new structures like quantum dots. Ram Shashedri on the phosphors used to convert the blue light to white. And then Chris Vanderwall is our theorist. And finally, Claude Weisbuch is here 3 months of the year, working with him on advanced light extraction structures. So just because you guys don't get a lab tour, just to emphasize again, UCSB has one of the largest clean rooms at a university with over 13,000 square feet. We have, I think, the world's one of the world's largest in-house MOCVD efforts at a university with 6 MOCVD systems. We actually have, I believe, 14 MBE systems. 2 of our nitrides, but how many? I heard Art say the number.
13.
13, okay. So 13 MBE systems. That might make us the world's leading academic research institute for MBE too, which is, I think, one of the main reasons why the Materials Institute or Science Department here is #1. Again, great characterization facilities. If you get any time during the break, maybe we can take you for a quick tour. Just to show you some of our goals, and I actually might skip this just because we're running a bit behind schedule, but I just want to mention the 2 goals for solid-state lighting and let Umesh cover some of the others. But our goal for solid-state lighting is to be able to do 280 lumens per watt by 350 at high current densities, and I'll explain what this efficiency number means in a few view graphs. Obviously, the thing that this can help address is the energy consumption. Not only is it going to stay flat, but it's going up. Just kind of wanted to point that out. But what I wanted to show is this just came out 2 months ago from the Department of Energy. This is the estimate of the savings that they estimate with LED lighting, where we're at 150 lumens per watt. So they didn't even add in our factor of 280 lumens per watt. But they believe by the year 2030, LEDs will represent a 46% savings, and this is the electrical consumption for lighting. So it's basically, the lighting consumption hasn't been going up, but we think we're actually going to drop this number, and there's been trends that it's already been dropping due to basically this is kind of the CFL being implemented, but now adding the LED on it. This 46% reduction in the energy needs for lighting is the equivalent of 51 gigawatt nuclear power plants. This is, by the way, in the US alone. So this provides us one of the low-hanging fruits we believe for energy savings. You could multiply this number by about 4 to 5 for the worldwide impact. So we believe LED lighting really is a real technology which is going to impact energy efficiency. Why it's so big is if you look at electrical consumption in California, which, by the way, is actually higher than national average, lighting actually accounts for 34% of the electrical consumption in California. By the way, that does not include the additional cooling power you need to cool a building which is being heated by incandescent lighting. And the actual, I just found out the load requirements are for every basically kilowatt saved by reducing the lighting, you would save a kilowatt on the cooling side. So I believe you could maybe even add another 5% on to the energy savings numbers. So I said I'd tell you what lumens per watt meant, but basically rather than plot efficiency here as a function of year, we plot something called luminous efficacy, which is basically the eye's response per electrical watt in. And if we look down here at the incandescent light bulb, this is basically where Thomas Edison invented the light bulb, and it's been stuck down here at around 10 to 15 lumens per watt. It's not going to change, and it hasn't changed for almost 100 years. The real impact on compact fluorescent is shown here. Basically invented in the 50s, came on pretty strong to the point that compact fluorescent, actually CFL is around 75 lumens per watt. This is the linear fluorescent, is about 100 lumens per watt. So the LED story, in terms of a historical sense, even though Tsuji came out with his breakthrough in '93, it took to about 2005, you could see, to really start to take off. And in the last 4 years, it's been an amazing research breakthrough after research breakthrough to get us up to now 152 lumens per watt in terms of R&D demo. On a manufacturing basis, we're at 100 lumens per watt. And in cases where you can't use fluorescent, which is generally a lot of applications indoor, but also any kind of directed application, you can see that at 100 lumens per watt, we already provide a huge opportunity from an energy savings point of view. And one of those directed applications is the downlight, which is actually what's right above your head right now. And what happens in that is you've got a compact fluorescent bulb in there, and it's at about 60 to 70 lumens per watt. But that fixture actually is bent metal. You actually redirect a lot of the light back through that, through the parabolic reflection here. You basically only get 58% of the light out of that downlight. So the actual efficiency of the compact fluorescent in this application, in this room, is 35 lumens per watt. The incandescent bulbs, 10 lumens per watt. An LED solution, today's version, is already 69 lumens per watt. This is heated with thermal equilibrium, driver efficiencies, that is the power conditioning, and the fixture efficiency. So with existing manufacturing technology, what I'm telling you, we're already twice as good as compact fluorescent and 6 times, 7 times better than incandescent. Market size, LED lighting is growing at about 25 to 30% a year. It's expected to be about a $50 to $100 billion market in about 8 years. There's still, I just want to point out, this technology hasn't, it's fairly well distributed in terms of countries. You could see Japan is one of the leading institutes, but also even Osram and Philips are number 3 and 4 in Europe. And actually half of Philips manufacturing is actually here in San Jose. Cree is a US corporation, they're number 6. and a lot of companies in Taiwan starting to come on. So the ranking of suppliers is fairly well distributed globally. You may have heard a lot about this. We can go country specific, but actually in terms of incandescent light bulbs, several countries have actually started to ban light bulbs. In the US, it's actually very difficult now to buy a 100-watt light bulb. You'll find in Home Depot, they actually put a sign there that by the end of this year, you won't be able to buy 100-watt light bulbs. So this is, there might even be some political repercussions in this. I hope it doesn't show up in the election, but the government is trying to motivate switching from these things which are 10 lumens per watt to our 60, 70 lumens per watt. We'll see how it goes. Some other countries have already banned it, and in Japan, LED lighting has actually taken off much faster than here in the US. So I just kind of want to point out why I think we're nearing that kind of curve where we reach economic viability. We're here now in 2012. We're sitting at about $10 for a kilolumen, and a kilolumen is what's put out by about a 60-watt light bulb. So that's the actual cost. People are charging, like I said, twice that. But that's at 100 lumen per watt efficiency. We've already demonstrated in lab actually 168, and I said we can get to 280. As we improve the efficiency, the actual LED package price is dropping quickly because you need less heat sink and you need less die area. So I believe we'll be at about $3 an LED light bulb within about 5 years. At that point, the cost to recover your payback basically drops tremendously. So I said maybe 6 months ago it was $40 an LED light bulb. It's already about 25 to 30. If we look at this as a payback period in terms of hours, this is the total cost of ownership for a 60-watt light bulb. Many of you may not know this, but if you run your light bulb a lot, that's why your mother told you to turn off the light bulbs. It's about $50 a year to run a 60-watt light bulb if you leave it on too much. So the 40-watt LED light bulb took, quite a bit of time if you only had it on a certain amount of hours, about 6-year payback. As we hit this projected $5 an LED bulb that I think will happen in 5 years, you can see for a normal user, which is about 1,000 hours, you'll get to your 1-year payback. So within a few years here, it would be a smart investment to start investing in LED lighting when you see it start hitting somewhere here between about $10 to $5 a light bulb. That's the point when it really starts to make economic sense. I don't want to go on the rebate program because we're running a bit behind schedule, I can see. But just it's starting to show up. And interesting quote here that Bill Hamilton from Home Depot observed is that LED lighting products are already about 10% of the company's retail lighting business. Turns out in cars, you might have noticed that the Audi had this nice little LED eye line, which they use for day running lights. It turned out it accounted to about a 1 mile per gallon energy savings in the Lexus 600H. This is actually getting to be pretty significant if you're getting 24 miles per gallon. The biggest thing, though, the reason why Audi LED headlights took off is because of the design feature. It gave them the ability to make this so-called LED eye line. Now Mercedes-Benz copied it, Lexus. So it turned out that lighting of the future will look very different than these big, huge fixtures you see today. Even in the organic space, they're making these big walls with these organic LEDs. I think you'll see a very different type of lighting infrastructure start to come about, and that's the industry we're hoping to help spur in the U.S. with some of these startups. So I mentioned this is just some of the return on investment arguments. I know we just heard about solar technology, but I just want to say from a federal return on investment point of view, there's only been $250 million federal dollars invested in LED lighting today. We've penetrated 2% of the lighting market, and we've already saved 4 gigawatts. And this just as comparison to solar technology over the last 30 years, we've invested $13 billion for about the same amount of capacity saved. So what I'm telling you is LED lighting today has already had about as big of an impact as solar cells have in terms of capacity saved. So here at UCSB, we're working on some of the major issues that still kind of haunt LED lighting. One of those is what's called the current droop factor, which is you can't take a little LED and just keep turning up the current and expect to get more light out. It starts to roll over in efficiency. One of those is due to heat. Turns out another one is due to some very complex physics, which we won't go into. But we're also working at extracting more light out of the chip, and we have several programs on that. So thermal droop drops the efficiency from these very high numbers by about 30% at the thermal operating temperatures of the LED light bulbs, which are actually pretty hot, about 120 C. Current droop of the chip is a bigger factor. Currently, most LED light bulb manufacturers operate here at around 10 to 20 amp per square centimeter. We would like to be out here at 60 to 70, but the problem is the LED light bulbs almost dropped by about half. So here at UCSB, we've actually made huge breakthroughs here. Some of this comes from the theory of Chris van der Waal, which identified that the electron density, or getting an Auger process where you get an electron being knocked up into a higher conduction band rather than emit light, led us to the idea that we should basically use thicker active regions or more quantum wells. Both of those things, let me skip this one, too much complex physics, basically improved efficiency droop from what it was in 2009, where we were seeing almost 40% droop, to today. These are some results from Suji's group. We're at only 5% droop at 70 amp per square centimeter. So this means you could take one LED light bulb and drive it a lot harder. So this helps reduce cost tremendously. Other things we're working on is complex light extraction technologies, making micro lenses, making nano patterns, even photonic crystals. This will help us improve the efficiency even further. Similar to solar cells, we actually developed some textured technologies where we actually put cones on the LEDs, both in the gallium nitride but also in the zinc oxide transparent conducting layers. This has given us very high extraction efficiencies approaching 80%. And this is some work we've been working on for over 10 years. So current LED extraction for our LEDs is between 80 and 88%, which is very good. We'd like to get that closer to 100%. Just show you some of the improvements here. The new LEDs with these transparent LEDs are basically shown you here. Whereas you put the current in, you can get more light out, whereas traditional LEDs tend to roll over. So in terms of actual quantum efficiency, this is actually the percentage of light that comes out for every electron injected. We're now sitting around 72% for LEDs made on our bulk gallium nitride chips. And this is from the early days of 2000, where it was only about 25%. So a lot of that curve that you saw go up in energy efficiency has been due to various chip innovations that have come over the past 10 years. And we hope to continue to even push this even higher and reach 90 to 95% efficiencies. Let me skip through that and just show you where we think we're going to with the 250 lumen per watt. Is we hope to basically move away from the current approach, which is a blue LED plus a YAG phosphor, to getting all three of the active regions on the same chip. That is a blue, green, red active layer. This would basically let you make an LED which has the highest efficiency. You can also even imagine functionality that this LED would be able to communicate. That is, you can transmit data with your light bulb at fairly high data rates, approaching a gigabit per second. Even newer technologies we're working on are these photonic crystal extractions, making a monolithic white sources with these quantum dots. All these iterations, I think, will require new iterations of CVD equipment. So we're proud to have Applied Materials as one of our newest industrial members of our Solid State Lighting Center here, and working with them on integrating some of these newer materials into the device. Finally, in the future, I think you'll even see laser sources used. And I might give credit again to Herb. All of these devices that we make use heterostructures in them. All of them have quantum well heterostructures, and we use heterostructures for the confinement layers and for the electron blocking layers. We actually have about 80 heterostructures in our more advanced LEDs for various reasons, lower contacts and stuff like that. Just showing you kind of where we think the future is going. Not only light bulbs, but we actually believe you'll start to see some of the base lighting show up just to some of the better color rendering. And Sandia National Labs, we're working with them, actually surprisingly shows you very high color saturated here on the left versus an actual incandescent lighting. And basically, with a 3-watt laser, they believe we can get to 270 lumens per watt. So these very high efficiency numbers we believe are achievable in the next 5 years with further research funding. And a final area, and interesting, had a conversation here at the break before the conference with some people. We believe, and gallium nitride can go down to these very low wavelengths for UV, you can actually make UV lights or light bulbs that help you purify water. There's a little handheld one, but where the power numbers really get big is basic industrial water purification or residential water purification. They were telling me about some enormous opportunities here in the UV for really saving huge amounts of energy, which are used for the current UV light sources. Let's skip that. I just have two more view graphs here. So turned out LED lighting for basically what I call off-grid lighting, and John Bowers is doing some work here in the Institute for Energy Efficiency, is basically combining an LED with a solar cell and a battery. If you do that three combination, you basically have a light source which doesn't need a grid anymore. And this is basically making a much bigger impact in the third world than it is here in the US. The US, the only application I've seen is the solar-powered garden lights. But in places like Pakistan and Nepal, there are already several thousand installations using LED lighting to basically help increase the ability to educate people at night and read books, which is currently being done by kerosene. So that's been a kind of an interesting thing that you wouldn't have imagined, wouldn't be possible without solar cells and without batteries and without LEDs. So in summary, kind of hope I've given you some of the exciting news about why we think LED lighting adoption will happen. Our main cost is then to get through innovation and scale, is to get the cost of LED lighting down to something that's commercially acceptable. Didn't have as much time as I would like to go through a lot of the novel technologies we're working here at UCSB, but with a fairly large effort, we believe we can continue to make improvements to get there. And basically, we believe this is very promising technology to reduce global energy consumption over 10% and save huge amounts of energy costs in the US alone and save a lot of pollution and reduce a lot of greenhouse gases. So thanks again for letting me give this talk. Thanks.